With this video, we will demonstrate some manual sclerochronological sampling techniques for isotope analysis at Mainz University. Essentially, we hold the slide with the sample in our hands during drilling and milling, with the wrist resting on the bottom. This gives stability. The sample needs to be perpendicular to the drill bit. There are clearly benefits of using an automatic micromill system by New Wave Mercantec, for example. We have such robots as well and use them for certain samples. However, the robot is slow and often produces stronger time-averaged data than the manual method. The reason is that the geometry of the growth patterns changes throughout seasons and ontogeny, and the growth front is often curved. By applying the manual micromilling technique, one can better follow the specific growth geometry and ensure that shell powder is milled off exactly parallel to the growth front. This is possible by observing where and how the growth lines strike out on three sides: the outer shell surface, on the cross-section, and at the surface of the inner portion of the outer shell layer. Our micromill consists of a low-speed drilling system produced by the company Minimo. This system consists of a transformer with a control wheel for the drill speed and a handset with motor. The motor runs at lowest speed at 600 RPM. The handset is firmly attached to a binocular microscope. Let's first have a look at the different portions in a cross-sectioned bivalve shell. As an example, we have chosen a glycemeridid shell. The shell was cut approximately along the axis of maximum growth, so that the growth lines near the most recent ventral margin of the shell were cut perpendicular. To the left of the sketch, you can see the hinge plate with dotted lines representing growth lines. Simultaneously with the hinge plate, the shell also grows in height by adding material at the ventral margin. The shape of previous ventral margins, when the specimen was younger and the shell smaller, can be reconstructed from the internal growth patterns. And again, the dotted lines are growth lines. The shell is divided into two shell layers, an inner shell layer, ISL, and an outer shell layer, OSL, which form in two different compartments, the outer and inner extrapallial spaces, respectively. Evidently, during lifetime, the growth rate decreases, and samples taken from the shell with the same resolution will represent increasing amounts of time as we take samples from ontogenetically older portions. So the time averaging per sample will tendentially increase from the umbo to the ventral margin. Samples can be taken by milling the inner portion of the outer shell layer from the outer shell surface, or by drilling or milling in cross-section. The latter two methods are explained here. Drilling and milling is typically completed in the inner portion of the outer shell layer. That is, the shell portion least likely affected by diagenetic overprint. When samples are taken by the drilling method, one needs to consider that shell portions closer to the outer shell surface grow faster than such toward the myostracum. So the time averaging increases toward the inner side of the shell. For drilling holes, we use a conical SIC drill bit that produces 300 micrometer sized drill holes. SIC is also known under the trade name Vidia, silicium carbide. We are using this type of drill bit also for micromilling shells on the outer shell surface, and can produce very narrow sample swaths of less than 100 micrometer width. To avoid cross-contamination, the drill or mill bit, as well as the sample surface, has to be cleaned with compressed air and a nylon brush prior to the first sampling step and between each sampling step. Micromilling is a more challenging task than drilling and is done at the growth front, typically starting at the ventral margin toward the umbo. Milling requires careful sample preparation. In particular, epoxy resin must be completely removed because even small amounts contaminating the shell material will change the isotope data significantly. The metal epoxy that we use typically flakes off easily from the shell, from the glass slide, as soon as we prick it. It takes a bit more time to remove the epoxy entirely from the shell. The next step is to prepare the inner portion of the outer layer at the growth front for the sampling. Our aim is to sample the colored portion in this sketch and remove the gray portions. It should not be removed too much material at a time so that the shell doesn't fall apart. I suggest to stepwise remove the gray highlighted portion while moving forward with milling. And here the outer portion of the outer shell layer is removed. It takes a bit, and once this is done, we also need to remove shell material underneath the plant sample surface. That is, between the glass slide and the shell, so that during milling the entire shell is sampled and contamination avoided. After this preparation step, a tooth of shell material is hanging in the air, so to say. I recommend that only 1 millimeter of shell is removed between the shell and the glass slide at a time, because otherwise the tooth may break off. All surfaces where shell material has been removed should be smooth and even. It can be very helpful to polish these surfaces with a flexible diamond polisher. This way one can recognize the growth patterns on all sides and get a detailed idea how curvy the growth front really is. With these guidelines, micromilling can proceed. The best way is to evenly abrade the growth front by moving the mill bit back and forth and using the growth lines on all three surfaces as guidelines for proper and precise milling. There are many different useful mill bits available. We typically use one which is 1000 micrometer in diameter, cylindrically shaped, diamond coated, galvanized diamonds actually, but there are also Vidia-based mill bits available which more gently abrade the shell material. This can sometimes be quite helpful. The last step is to collect the shell powder. I personally try to collect the powder directly into the brass metal vials, but others prefer to collect the powder on weighing paper. Once the sample weight has been determined, the vials can be placed into the tray. Each of our trays accept 60 vials. For shipment, the vials need to be protected with a sheet of aluminum foil. On top of that comes a rubber sheet and the lid. The lid is affixed with 6 screws, which need to be placed into the holes in the order shown here. First, the 2 screws in the center are loosely tightened, followed by the 4 screws at the edges over cross, slightly tightened only at this time. And then tighten the screws in the center a bit more, followed by tightening the screws at the edges. But do not over tighten them, because otherwise the aluminum tray will be destroyed.